Okay, so what we are talking about today is sampling distributions for mean. So we've talked about sampling distributions in general before, and then we looked more specifically at proportion. We did that, we said, because proportion is an unbiased estimator and it is used for categorical data. We're going to look at sample mean. The reason we do that is sample mean is an unbiased estimator of population mean, and we use mean for numeric data. So it's going to be very similar to proportions. We're going to talk about the center of the distribution, the shape, the spread, and then we'll do some calculations. This is the page I need you to find if you have not found it already. Just jumping right in, we are looking at sampling distribution of sample mean, so the sampling distribution of X bar. Talking about the center and spread of the distribution. We already saw this when we did the basketball players. We saw that if we took all of the sample means and averaged them up, we would get the population mean. And that is because X bar is an unbiased estimator of population mean. So if we take all of the sample means of all samples of the same size, average them up, we're going to get the population mean. Again, what that means is over time, sample mean will not over or underestimate population mean. And then standard deviation we talked about also. That is the standard deviation of the population over root n. And this is the one that has a special condition. This is only if our sample size is less than 10% of the population size. I would tell you on your quiz, at least half of you didn't check that. So I would star that, bold that, highlight it, because a lot of us are forgetting to do that. One really important note for you is notation matters. Either use it correctly or don't use it at all. What I'm referring to is these symbols, or even the formula. If you're not positive on the notation, just use numbers. Because if you use the wrong notation, it is going to be counted as wrong on the AP test. Okay, what is the shape of the sampling distribution of sample mean when the sample is taken from a normally distributed population? This is what we saw with the basketball player heights. The heights were normal. The sampling distribution then was also normal. So if the population is normal, then the sampling distribution, or the distribution of X bar, is also approximately normal. That word approximately is really important on the AP test. If you write the distribution is normal, you're not going to get credit. If you write approximately normal, you'll get credit. So you have to put the word approximately. If you're not sure, just always put it. Does sample size matter? No. No, sample size doesn't matter. I do want to remind you that there is a difference between the sample, the population, and the sampling distribution. So we've talked about many times before, a distribution in general shows us all the possible values and how likely they occur. So the three different distributions, we could do that for a sample, population, or a sampling distribution. The sampling distribution is the one on the dot plot where every dot represents an entire sample of the same size. Are we tired today? Yeah, me too. Okay, we're going to finish this page and then we'll take a break. At the Nutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Okay, before we even read A, looking at our numbers, mean 16.1, standard deviation of 0.15. This is for each jar, and we're approximately normal. So if we pick a jar off the shelf, we expect it to be around 16.1 ounces. Without doing any calculations, which outcome is more likely? Randomly selecting a single jar and finding that the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average is less than 16. Discuss with the person next to you. Which one do you think is more likely? Okay, what do you think? Which one is more likely? A single jar less than 16 ounces or 10 jars with an average less than 16 ounces? Luke, thank you.
Okay. I'm going to say a single jar that's less, because you have to be consistently pulling ones that, if you're selecting 10 for them to average out to be less, a good portion of them will have to be less, and you have to make sure and then you also have to not get any outliers in the too high direction. It's a lot more up to it's a lot harder to get an average of less than 16 for 10 than just pulling one that weighs less.
Do you guys agree? Yeah. Okay, so I like the way you explained that. For the average to be less than 16 ounces, we would have to consistently be pulling jars that are underweight. So which one is more likely? Single jar. Because averages are less variable, they have less spread, less variability than individual measurements. Okay, find the probability of each event described above. So if we let X be the weight of a single jar, we were told that X is approximately normal and that the mean is 16.1 and the standard deviation is 0.15. We want the probability of a single jar being less than 16 ounces. Since you have your calculator out, can you do normal CDF right now and figure out what that is, please? So go to normal CDF. Figure out what is the probability of a single jar being less than 16 ounces. Did we get about 0.25?
Give me a second.
Okay, this is the bare minimum amount of work that you should be showing. Instead of this line and this line, you could also have a figure that is well labeled and shaded. Now, the second one asked for 10 jars with an average less than 16. So in that case, we're looking for the probability that X bar is less than 16. Because the population is normal, X bar also has an approximately normal distribution. The mean of X bar is the same, it's still that 16.1. The standard deviation, though, we got to take that 0.15 and divide by the square root of n. So now we should see that we're going to get a smaller probability because our standard deviation is much smaller. Can you now calculate that using normal CDF in your calculator? So it's almost exactly the same calculation except you're using a new standard deviation. Those of you who've done this, you should have gotten about 0.0175. Yeah, we agree? Okay, I said we were going to finish this page and then we would take a break. The most common error is that students use the wrong standard deviation. And that's because they forget to divide by the square root of n. Two more things I want to talk about and then we'll take a break. Oftentimes, students will use that 0.15 divided by root 10 in their calculation. But they put 0.15 on their figure. So they'll use the correct standard deviation in their calculation, but then put the wrong one on their figure. So what College Board does is College Board considers that a parallel solution, considers it giving two solutions. So even though you got the correct probability, you would be marked incorrect because of the wrong number on your figure. And so we have to make sure we use the right standard deviation and also put the right one on the figure. Last thing I want to say real quick. Instead of doing this calculation, a lot of times when people see this question, what they'll do instead is they'll find one jar and then they'll say, okay, well, I'm just going to raise that to the 10th power for all 10 jars. It doesn't get you the same answer. What does that probability represent if I take 0.25 and raise it to the 10th power? Josh?
That all of them are under 16 ounces?
That all of the 10 jars are under 16 ounces. Yeah. So, that's why you can't use that one. Okay, so of course what you should be thinking is, but what happens if the population is not normal? What do I do? And I'm so happy to answer that question for you. Okay, so what happens if the population is not normally distributed? Well, there's two different cases. For a small sample, or for small sample sizes, that is anything 30 or below. So if we're taking samples of size 10 over and over and over again, that's considered a small sample. X bar then will follow the population shape. For large samples, again, that is anything bigger than 30. That is when X bar has a normal distribution. Approximately normal. So in the case of the peanut butter jars, sample of size 10 was normal because the population was. If I hadn't told you, though, that the population was normal, we couldn't have done that question. So if we don't know the population, we need to be taking large samples. This does not mean we are taking 40 samples, for example. It's referring to the size of the samples. Size of the samples. Okay.
Sample of 40 instead of 40 samples.
Yes, exactly. This rule right here, this is big, is called the central limit theorem. So sample mean is a little bit more difficult than proportion, because proportion you're always going to do n times p, n times 1 minus p. That's always going to be the case. Whereas you kind of have two different ways to check for normality with mean. Okay, let's do an example. We have a few more things to talk about, then we will be done with notes. Suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assume that students at your school are typical texters, and you randomly select 50 students from your school. Calculate and interpret the standard deviation of the distribution of X bar. Okay, so standard deviation of X bar. Standard deviation of the population, which is 35, divided by the square root of n, which is 50, gives us a standard deviation of about 0.495. This is the standard deviation of X bar. So if we were to take X bar measurements over and over and over again. So if we were to randomly select $50 students and what are we asking them? Number of texts that they sent in a day. If we were to randomly select 50 students and ask the number of texts sent in a day, I'm going to say again and again. Does that make sense? Like I'm selecting 50 students again and again?
Many times.
Sure, many times. The average number sent, and that average, this average number sent, that's X bar. Right, so that is the mean of just that sample. The average number sent will typically deviate from the population mean, so that's mu, number sent, by 4.95 messages. So we're referring to two averages here. The one average comes from the sample, and then that's typically how far it's going to be from the population. Okay, part B. What is the probability that these students have sent more than a total of 1,000 texts? So we are looking for the probability that the first student add the second student add all the way up to the 50th student together have sent more than 1,000. Or a total of more than 1,000. Now, we've done that before. You all have seen that before. We could do this as a combination. So we could consider the total to be a variable and find the mean and standard deviation of the total. Or what we can do instead now is do this as a sample mean. So if we have 1,000 texts sent by 50 students, that's an average of 20 per student. So that's the same as looking for the probability of an average being greater than 20. Okay, what do we know about X bar? Well, first of all, we know that X bar is normal, and that's because our sample size is 50, which is greater than 30. So it doesn't matter that the population is right skewed. We know that the mean of X bar is just that 15, which is the mean of the population. And then the standard deviation we already talked about or did previously is 35 over root 50. Okay, that is a total of about 0.1562. Not a total, that's a probability of 0.1562.
I just did my calculator. When it comes like
Yeah, you can
What
change, you can do it that way. Yeah.
To get the positive number I want.
Okay, we feel okay on those?
Yep. Just
Okay. I'm not gonna write, we're just gonna talk. Well, I'm gonna talk, you should probably write. Let's talk about what these symbols are. What is this symbol? Mu, what does that stand for? Population mean. So this symbol mu is population mean. This one is sigma. What does sigma stand for? Population standard deviation. So we have population mean, population standard deviation. You have to write the word population. If you write mean, it's wrong because that's just not specific enough. What is P? Population proportion. Population proportion. What is N? Little n. Sample size. X bar is sample mean. P hat, sample proportion. And then these are the symbols that students tend to mess up. What is this first one that has a mu and an X bar?
Isn't that what we were just doing?
It is. What would we call that?
Sample mean?
What's X bar? The mean of all the sample means, the mean of the sampling distribution. So what this one means, if I found all sample means of samples of the same size, so I took all the samples of size 10 peanut bars, if I took all samples of size 10 of 10 peanut butter jars and averaged the weight, and then averaged all of those averages. This is the mean of the sampling distribution of P hat. So if I averaged up all the sample proportions, and then those are my two spreads. Again, notation's important, so either use it correctly or don't use it at all. I have one last thing to talk about, and then we are done with notes. Last thing I want to talk about is P hat and X bar. So we're going to make ourselves a little table here. About P hat and X bar, I need you to know I'm going to do P hat. I need you to know the center. I need you to know the spread. We need to know the shape, and we need to know any conditions that apply. So we're going to talk about this for P hat and for X bar. Okay, the mean of P hat is equal to the population proportion. The mean of X bar is equal to the sample mean. Right? That's pretty much the same idea. That's because both are unbiased. The condition is also going to end up being the same. So the only condition is that our sample size has to be less than 10% of the population size. And what is that related to? Anyone? Thank you, standard deviation. It's related to standard deviation. For our standard deviation formulas, for P hat, it's the square root of P, 1 minus P over N. And then for X bar, what we just found, population standard deviation over root N. These formulas are all on the formula sheet, and I'll show you that in a minute. So you need to just be able to identify which formula to use, but those you don't need to have memorized. The conditions are not on the formula sheet, and the shape is not on the formula sheet. Okay, the shape, I think, is the big one where it differs. For p hat, distribution is going to be approximately normal if n times p is at least 10 and n times 1 minus p is at least 10. Proportion is nice because you're always checking those two inequalities. That's it every time. X bar is normal if the population is normal or we are taking samples that are bigger than 30. And those samples bigger than 30, again, that is called the central limit theorem. You will see that theorem. That's like a huge theorem in statistics. So that is one where I actually kind of need you to know the name. And then the last thing is really, this is approximately normal and approximately normal. Again, if you're not sure, just write approximately, because if you do not write approximately on College Board, you're gonna lose credit. Notes, done. Questions for me? Last thing I wanted to talk to you about is I wanted to remind you what the formula sheet looks like. So this is what I'm saying when I'm saying the formula sheet has the formulas on them. Right now, we are talking about sampling distribution. So you just look, I have one population proportion, I'm talking about the sampling distribution. It tells you what the formulas are, and then it really gives you a hint as to what those symbols are. We are not talking about this yet. We will get here eventually, but not until second semester. And then down here is for the mean. So again, this helps remind you what the symbols are, and it gives you the formulas. This is on the back of the first formula page. Does that make sense?